Alrighty, hi everyone. Welcome to the Ice Giant Systems seminar series. This is previously the Neptune Triton system seminar series, but hopefully most of you saw that the sort of scope of it expanded a little bit. It changed a bit after the decadal survey came out, and so we always, of course, always allowed analog objects from Neptune, such as Uranus, and of course any of Uranus's moons, ring systems, things like that. But I think certainly after the decadal results were published, we decided to expand things a bit. So we're now the Ice Giant Systems seminar series, and so welcome everyone. And I'm just gonna, apologies again for the incorrect link. I'm gonna figure out how to change that for the next one. So hopefully it won't be invalid, but I appreciate that you all were able to make it today. And so I'll give Jason just a quick introduction, and then I'll have him go ahead and get started. So Dr. Jason Hofgartner received his PhD from Cornell University, studying phenomena in the lakes and seas of Saturn's moon Triton, where he led the Cassini radar team in the first discovery of transient features in the seas of Triton. He then went on to work at NASA JPL as a postdoc and then as a research scientist, modeling volatile transport on Eris, and he led the team on New Horizons, searching for temporal changes on Pluto and Charon. Dr. Hofgartner also conducted remote sensing tests to distinguish between competing hypotheses for plumes on Neptune's moon Triton, which spawned the work that's going to be presented today. He's currently a senior research scientist at Southwest Research Institute in Boulder, Colorado, where he studies surface features on Pluto, seasonal volatile transport on Eris and other KBOs, and Cassini radar observations of Triton. So thank you so much for joining us, Jason. And you've got your slides shared. So feel free to go ahead and take it away. And I'll turn my camera off just for now, so I'm not distracting
Sure.
on you. I'll come back afterwards, but go ahead and take it away.
All right, thanks, Jody, for the introduction and for organizing this. Discussion is welcome. So, if you have clarifying questions, please feel free to jump in, and even to start discussion would be great. I wanted to say on this title slide that I've recently changed institutions. So as Jody mentioned, I'm now at the Southwest Research Institute in Boulder. And then I also, of course, want to say that this is very much the work that I'm presenting is a team effort here with many different contributors listed there. And this actually has been a very multi-year project. About 3.5 years we were working on this. So a lot of different exchange of ideas with the team. The work is now published, so all the details are available. And this image that I find very inspiring of Triton was produced by Michael Carroll. So the outline for the talk is that I will briefly introduce Triton and its plumes, and then I will talk about the sort of main eruption hypotheses. There's three. There's many variants of different hypotheses for the plumes of the eruptions, but we'll sort of put them into three buckets that I think are kind of distinct hypotheses. And then we're going to really dive into the weeds here in section 3 and scrutinize some of the key evidence for the solar-driven hypothesis. And then we'll back up a little bit and talk about how remote sensing tests in a decently straightforward way can actually very confidently distinguish between these hypotheses that remain. So to start, Triton is the largest moon of Neptune. It was likely captured into orbit around Neptune from the Kuiper Belt, and it's a bit smaller than our own moons. This is a very large world in its own right. However, it's only ever been explored with a spacecraft back in 1989 when Voyager 2 flew through the Neptune system. And in that brief encounter, Voyager 2 discovered Triton to have a very young surface, and that's based on the relatively few impact craters on the surface. Triton is among the youngest icy surfaces in the solar system, possibly even the youngest of all. And also an enigmatic surface in the sense that there are morphologies, features on the surface of Triton that hadn't been seen before and still have never been seen since. So they may be unique to Triton and are certainly enigmatic. So it's a very exciting surface, in my opinion, especially for those two reasons. In addition to spacecraft exploration, of course, ground-based telescopes, Earth telescopes have been researching Triton, and one of the main points that I'll highlight from that work is that we know that Triton has an abundance of seasonally volatile ices. So these are icy materials that are moving around with the seasons on Triton. And that includes nitrogen, carbon monoxide, and methane. And then in addition to those seasonally volatile ices, there are much more refractory ices, including water and carbon dioxide. So a real rich chemistry in terms of material properties. And okay, yep, feel free to post questions. I can see the chat, so I'll try and monitor it. I'll do my best, but like I said, feel free to interrupt me. So on the right is kind of one take on why Triton is an especially interesting object, in my opinion, and that's because it's at this intersection, most likely of Kuiper belt objects, so probably formed in the Kuiper belt, and then was captured into orbit around Neptune. Triton likely is an ocean world in the sense that it has a liquid water ocean underneath its subsurface, in the subsurface underneath its icy layer. That's most likely the case, but we have not confirmed that. And then Triton is certainly an active world. There was even activity observed sort of over 45-minute timescales during the Voyager 2 flyby. And of course, we're going to talk more about that. So Triton is not unique at that intersection. Most likely, Pluto and a Kuiper belt object called Eris are also in that category of those three worlds. And so in many ways, these three, Triton, Pluto, and Eris, are a triplet. They're a real useful set for comparative planetology because they have a lot of characteristics that are very similar, and then some that are different that kind of teaches us about those processes. So in the same way, comparing Uranus and Neptune with such similarities is valuable, or Earth and Venus, Triton, Pluto, and Eris are a real nice set for comparative planetology. And so for example, they're all out in the distant solar system. Triton is around Neptune, shown here. Pluto is in the Kuiper belt. It actually comes closer into the sun than Triton at times. And then Eris is a much more distant object, usually, but actually comes in closer than Pluto at times. So their orbits crisscross. They have roughly similar radii. Triton is a little bit bigger than the other two. And they're all a mixture of rocky material as well as abundant icy material. And then what really makes them sort of a distinct group, a trio, is that all three of them have a lot of nitrogen ice on their surface. And that nitrogen ice participates in sort of seasonal movement, possibly movement from interior heating as well. And then there's methane that goes along with that nitrogen too. And that methane and nitrogen results in very bright surfaces for Triton, Pluto, and Eris, some of the brightest surfaces in the solar system intrinsically. So just to go to that point a little bit longer as part of that sort of context for Triton, this is the way I like to think of it. These three worlds have very similar initial conditions. Most likely that's because of those bulk characteristics are indicating that they probably formed very similarly, but then they've all had very drastically different evolution. So each of them has in their history had a singular event of severe perturbation that significantly affected their evolution ever afterward. So in case of Triton, that was captured by Neptune into its orbit, and that has, of course, resulted in probably a lot of tidal heating and significantly affected it. Pluto almost certainly experienced a giant impact that resulted in the formation of its moon Charon, so binary planetary system, and that giant impact, basically really changed how the flavor of that system. And then Eris, way out in the distant solar system, was scattered there probably by a giant planet. So this is a little bit dark, but a way to think of this is that in this triplet, Triton is the kidnapped triplet, Pluto is the abused one, and Eris is the orphaned one. And so that kind of gives you context that these are significant events that have affected their flavor. And so only by comparing them can we better understand their initial state, because we don't get any one of the three in kind of its unperturbed, unaffected state. And then we can also, by comparing them, understand these processes that are severe planetary processes that, of course, we'd like to understand in a general sense. And then probably all three of these perturbations are related to the movement of the planets in the solar system. And so they may give us a hint about that dynamical rearrangement. So I've attempted to kind of nibble away at this problem, which I think is really ripe for some fundamental planetary science in a series of papers shown under the pictures there. Okay, so moving on then to introduce the plumes. So the plumes were observed during the Voyager 2 encounter back in 1989, and shown on the right here is a blink between two different images where the spacecraft position has changed. And so the parallax from that changing position of the spacecraft you can see this long, dark cloud. It's about 150 kilometers long, that it looks like it has moved relative to the background. And that's again, the parallax, because that cloud is about 8 kilometers above the surface. And then those who have studied these images extensively interpret this here to be a link between the surface and that cloud, which is the erupting plume that is creating this cloud. And this cloud in different images, these are not the only 2 images of this cloud, but are probably the 2 best. Between different images, there's interpreted to be basically, variation in this cloud that indicates, how it's moving with the wind, and that the eruption is not just, a perfectly continuous eruption, but has, variability as you would expect. And that's seen over about a 45-minute time scale with the Voyager 2 images. And there are 2 plumes that were confirmed on Triton, and the definition of confirmed in this case is basically that there is a connection that could be observed between the cloud and the surface. There are 2 others where basically they're very close to these, but just off the horizon, and so that connection was sort of partly observed, but not completely down to the surface. So they're almost certainly plumes as well. And then there are about a dozen other candidate features with varying degrees of resemblance to these plumes. And so, these may not just be sort of singular events, but maybe in fact quite frequent on Triton, excuse me. Okay, so in addition to the plumes that were observed, Voyager 2 also observed these features on the surface that are fan shaped. So they kind of have a central point, and then they grow outward from that in a fan shape. And they are relatively dark. Some of them are shown here in the image on the right. They're actually intrinsically quite bright. These are very bright features, but they're on this very bright background, and so they're relatively dark. And they were abundant on Triton. About 120 were mapped in Voyager 2 images of about 40% of Triton's surface has sufficient resolution and quality to do the mapping. And so they're quite abundant there. They vary in their scale. Some of them are quite small, less than 5 kilometers in length, to others, such as this large one here. I hope you can see my cursor, is well over 100 kilometers in length. And these are widely interpreted to be deposits from former plumes. And so we're going to go with that assertion, or that putative relation in this work. But I do, always try to remember to note that link has never been fully established. And if they are from former plumes, they're actually very valuable, because with just a few plumes observed with the imaging that you saw on the previous slide, as you can imagine, the constraints are relatively limited. And so these fans actually provide a lot of additional constraints on the hypotheses for the plumes. Another maybe interesting thing to note about the fans is that they generally always have a northeast direction from their point. They move out towards the northeast. The plumes actually move out from their point towards the west. And that's readily explained as being due to changes in the wind direction with altitude. So when the plume is erupting, they're nice and high at 8 kilometers and experiencing a wind that's moving towards the west. As the eruption dies down and they're at lower altitude, they experience a northeast wind. And these fans, I said there's 120 of them. They always occur within this very bright region that is extensive across the southern hemisphere of Triton. So the SHT stands for Southern Hemisphere Terrain. This is its northern boundary up here. Basically covers most of the southern hemisphere, and the fans are always in this region. So this is a map here of the southern hemisphere terrain. This sort of dotted feature here that covers most of the map is the southern hemisphere terrain. You can see that in one place it actually reaches the equator and even goes slightly north of the equator, but it generally covers the vast majority of the southern hemisphere, the vast majority of the southern hemisphere, and so hence is called the southern hemisphere terrain. This region was initially interpreted to be a nitrogen polar cap, for good reason. Nitrogen was known to be on the surface of Triton from Earth observations. Like I said, it's very, very bright, and that's where you expect nitrogen to accumulate. But that is more recently contested, and so we're going to talk more about that shortly. Okay, so that's my introduction to Triton and to its plumes. And so now we're going to move on to talk about the eruption hypotheses. And so if there's any questions about the first section, feel free to jump in. Okay, so the eruption hypotheses. So there are sort of three main hypotheses for these plume features. One of them is the solar-driven hypothesis, also called the solid-state greenhouse hypothesis. So the idea of this hypothesis is that nitrogen ice is relatively transparent to visible light from the sun, and so that light penetrates through the surface of the ice, and then is either absorbed at the base of the ice, possibly with a dark substrate to enhance that absorption, or it can just be absorbed within the ice itself if it's thick enough. The dark substrate is called the super greenhouse model or super solar driven, and then absorption within the nitrogen ice, just complete absorption there, is called the classical solar driven model. And so the nitrogen ice then is more opaque to the infrared light that gets emitted, the thermal radiation. And so you have a greenhouse effect there, and that results in heating within the ice or at its base. And because nitrogen is such a very volatile material, even just a little bit of heating, difference of a few Kelvin, which is readily easy to do with the amount of sunlight there, that results in a significant pressure increase. So you can build up this pressure within the ice, and then eventually that explosively erupts onto the surface and produces the plumes and fans that we see. By the way, I should say that some of the most fun I had on this project was working with very talented artists, including Lisbeth and Lisa here, that produced these images. So the second sort of main hypothesis is the cryovolcanic hypothesis. So I think of this as sort of an icy analog to volcanism on the Earth. There's, again, different variants for this hypothesis, right? It could be sourcing a subsurface ocean that may be on Triton, or it could be sourcing a more near surface chamber of liquid material. But the basic idea is that this is, like a volcanic process that's occurring in this icy material. And that may or may not occur on the nitrogen ice region. It really has no preference. So the plumes can occur away from the nitrogen ice or, within the nitrogen ice in this cryovolcanic model. And then the third model is, aptly named the volatile ice. So volatile ice here means nitrogen ice in a more generic sense. It could be adapted possibly to methane or carbon monoxide. It needs a sheet, so a very thick layer, and that's to cause a lot of insulation for heating from beneath, basal heat. So instead of being solar driven, the heating is coming from below, possibly tidal, possibly radioactive decay. And then a thick layer of nitrogen ice is insulating that heat. And so that results in one variant of this model in melted nitrogen, which when it reaches the surface, results in these eruptions. Or in another variant of the model, both of these are published in different works, the heating results in a solid state convection, and the heat is transported that way. And so that one we'll call the volatile ice sheet basal heat model. So an ocean is shown in all three of these hypotheses, but is not necessarily required for any of them if such an ocean is not present. And I should say that there are some non-eruption hypotheses that have been considered, but they generally struggle to match the observations. In particular, the sort of straight column rising up to 8 kilometers. And so it seems very likely that these have to be an eruption of some form. So again, lots of fun working with some artists. And so I got to help them produce this animation. So this is just an animation of the solar-driven model where the sun causes this heating within the nitrogen ice. That heating results in volatility that builds up pressure. So you get this nitrogen vapor that's building up within the ice that then explosively erupts out into the atmosphere and surface. And then different directions in wind height result in a direction for the plumes going one way. And then when those eruptions finish, we don't know the time scale for that or for how long they last. Eventually that material gets deposited onto the surface. Time scale could be, really anything that's longer than the hours that the Voyager 2 encounter saw. Okay, so at this point, I want to sort of jump into the weeds and really talk about the solar-driven hypothesis. This hypothesis was the first hypothesis proposed. It is by far the most studied hypothesis, and I think before our work was largely considered to be the leading hypothesis. And what we're going to do is sort of based on our work, we're not going to say that the hypothesis is not viable, because I think it's a good hypothesis still and works, but really should not be the leader. And really, all of the hypotheses have pros and cons, and should be considered further, in addition to new hypotheses. So the sort of four main lines of evidence for the solar-driven hypothesis that maybe were arguments for its leading position before are the existence of the southern hemisphere terrain, which again was interpreted as a polar nitrogen ice cap. The plumes are actually similar in latitude to the subsolar latitude, where the sun goes directly overhead during the Voyager 2 encounter. So that's where the solar heating instantaneously is most intense. And so that kind of motivated the solar model. In addition, the fans, their distribution was generally north of the plumes, which is exactly where the sun had been prior to the Voyager 2 encounter. And so you could imagine that the sun had sort of been causing these migrating eruptions as it moved. And then much more recently on Mars, an analog to this process using carbon dioxide rather than nitrogen, because Mars has carbon dioxide in its atmosphere abundantly and on its surface has an ice. This process is known, this sort of solar-driven process does occur on Mars, and that is well established. And so it makes it more easy to digest that it could be occurring on Triton as well. So that's the most studied and previously considered leading hypothesis. And so let's dive into each of those four arguments. So first of all, this is not an argument that comes from our work, the first one, but rather from others previously. So the southern hemisphere terrains may not be volatile-rich. So again, it's a very bright surface. We know that there's nitrogen ice spectroscopically from Earth observations, but the Earth observations do not strongly constrain where that is. And volatile transport models suggest it would accumulate at the poles. And so this southern hemisphere terrain was initially interpreted as a polar cap, but in more recent Earth-based observations, basically by watching Triton rotate, the change in how the nitrogen and other ices spectroscopically vary with that rotation is argued to be more consistent with the southern hemisphere terrains as more refractory rich. It's important to note that these observations were not at the same time as the Voyager 2 encounter. So if this was just a purely seasonal deposit, then it could be, that it was seasonally nitrogen and then is gone at the time of those observations. And then more recently, the latest, greatest state-of-the-art volatile transport model, again, looking at lots of different possibilities and reasons why nitrogen might not accumulate at the southern polar region. The conclusion is that nitrogen really wants to do that, and so in my view, it's undetermined what the composition of the southern hemisphere terrains is. And so that's exciting, more work to be done, but really it can't be, in my view, considered then a strong argument for the solar-driven hypothesis, given that we don't know that it's a polar cap. Okay, so the plumes, the two plumes that were confirmed had a latitude of 49 degrees south and 57 degrees south. And the subsolar latitude at the time of the Voyager 2 encounter was 45 degrees south. And so that similarity, again, was considered possibly indicative of a solar-driven model. It's interesting to note that, in fact, that similarity is not actually a prediction of the solar-driven model. So shown here in the figure is the average amount of energy received over the course of a day. So as Triton rotates completely, the total energy received relative to if the sun was shining directly overhead. And then on the bottom axis is the latitude on Triton. And so if you look at the black curve here, this is where the subsolar latitude is right over the equator. So of course you get the most sunlight at the equator. And then as you might expect, that drops down to 0 right at the pole. Now, if you move the subsolar latitude to say 10 degrees north, the peak of that point also moves northward. It doesn't actually move exactly to 10 degrees north, but relatively similar. And then you get this bump here in the polar region. And that's due basically to the fact that that polar region is getting illuminated throughout the entire rotation. So on Earth, it would be 24 hours a day, the whole rotation period of Triton. As you move further, the sun further, say 20 degrees latitude, that polar term, again, this term rises, that polar term starts to increase. It actually starts to become comparable. This isn't really necessarily intuitive to us, but if you've ever been to like a very high latitude region in the summer that's not ice covered, it's actually quite warm. I've been to northern Canada, and it's not that different, say, to parts of the US or Canada in the summertime. And then, what's not really intuitive to us, but is actually quite common in the outer solar system, is that subsolar latitudes can rise very high. And as it does, the polar term really starts to dominate and very quickly overcomes, all other of the heating. And so, in fact, it's the pole that is receiving the most sunlight throughout the course of a day. So on the plot on the right is the exact same plot as on the left, except that now I've moved the subsolar latitude to 45 degrees in the southern hemisphere. And then, so this is the heating. And then the green lines indicate the latitude of the two confirmed plumes. And you can see in this plot that there's really nothing special about the solar heating at that latitude. I mean, it's near an inflection here, but that's not special anyway. And it's not really necessary that you would predict the plumes to be occurring at this latitude. They could be really occurring anywhere that there's all this heating, and probably more likely even at the polar region. So, you can make, this is not a full-scale modeling of the solar-driven hypothesis. You can make these latitudes sort of special and the most likely to occur for plumes. But in order to do that, you really have to fine-tune the properties of your solar-driven model. And so, the model works, but this is not an argument in favor of that model. And that's the point here. Okay, this is just a particular detail it's a rabbit hole that I love to dive down. Albedo actually varies with incidence angle. I didn't appreciate that until much more recently after many physics courses, but albedo actually can vary with incidence angle. And so that was an effect that we considered. It's actually measured for Triton. That's the stars here. You can see the albedo dependence on incidence angle is very weak. And so, when we did do this calculation for these albedos, it basically negligible difference and not even appreciable in the plots. We also considered much stronger variations with albedo. This is a very extreme dependence, where albedo can run from 0.3 up to unity with incidence angle. And when we do that, we find, that qualitatively, the shape of the curves changes a little bit. If you compare this blue curve, for example, to this blue curve over here, it changes, but it doesn't change the main conclusion that there's really nothing special about the latitudes where the plumes occurred. And we consider a whole variety of different profiles in albedo with incidence angle. Okay, so then the third point is the geographic distribution of the fan. So the shown on the plot here now is a projection of the southern hemisphere of Triton. So you're looking straight down at the south pole of Triton. That's right here, and then this whole side is basically the part that faces Neptune. It's the sub-Neptune hemisphere. That's the side that was imaged in high resolution by Voyager 2. The location of the plumes and their fan and their clouds is shown with the two green marks, and then all of the locations of the fans, the 120 of them, are with the black marks. The boundary of that southern hemisphere terrain, the SHT, is shown by the cyan line here, and then the actual subsolar latitude at the time of the encounter is given by the blue line. And again, so the idea was that this blue line had previously been further up, and then as it was moving down, it was causing these eruptions to migrate. And so that was sort of the argument in favor of the solar-driven hypothesis, that you would get these former eruptions evidenced by the fans, the current eruptions more poleward of the subsolar latitude. It turns out that after really scrutinizing this, I think an equally valid interpretation of this distribution is that the fans basically fill the southern hemisphere terrain. They're basically just this abundant feature on Triton that seems to really fill the southern hemisphere terrain, or at least the southern hemisphere terrain that is on the side facing Neptune. And then the basically imaging, the biases in the imaging, the quality of the imaging result in much weaker, much poorer imaging at the polar region, a very strong resolution boundary over here, and sort of a fuzzier resolution boundary going this way. And so that interpretation is totally consistent with the data as well. So both those interpretations are true. And so, the geographic distribution of the fans is not necessarily an evidence for this solar-driven hypothesis. So we, like I said, really dove into the weeds with that a little bit. So just to show a little bit more quantitatively, on the right is a plot of the frequency of fans with latitude. And so you can see basically it rises up as you go towards the pole, and then probably flattens out. And then around here, although it's showing a decrease, in the number of fans, that may again be a bias of the quality of the imaging towards the polar region. And then also shown in the orange curve is the basically the amount of area, the number of longitudes that are covered by the southern hemisphere terrain. And so, there is a little bit of southern hemisphere terrain right at the equator. And as you go more and more towards the south, basically the southern hemisphere terrain completely covers all longitudes. And so the point of this figure is that the shape of these two rises is very similar. And so I interpret that as possibly being that, again, the southern hemisphere terrain is basically controlling the existence of the fans, like where they occur. And so that's why we see that rise in the fans there. And then the southern hemisphere terrain, you would predict basically that there would be lots of fans towards the pole as well. And the imaging, we don't know yet if that's the case. By the way, this basically relation holds whether I take, the whole sub-Neptune hemisphere, or if I take particular wedges, sort of pie slices, and basically it's still true, always the case that these hold. And then there's roughly correlation again, if we do the same thing, but do it with longitude. So the relative frequency of the fans going as a function of longitude, where you're considering all latitudes. And what you can see is that, there's some variation in the abundance of fans, and that variation roughly follows the southern hemisphere terrain, and then it breaks here. So the point is not that the blue and orange curve, are at exactly the same location, but rather that they have roughly the same shape moving from right to left. As I said, the boundary here to the east is a very sharp resolution boundary, and so I'd expect them to be better correlated here. And then there's sort of, because Voyager 2 basically as it approaches Triton is taking ever better resolution images, this boundary becomes sort of, just this slow decreasing resolution moving towards the west. And so that's probably why that lack of correlation is falling there. So basically, again, just to summarize, the geographic distribution to go to the fourth point, that the solar-driven process occurs on Mars. It might have been that there was analogous plumes on Pluto. That's not the case. I have looked closely with the New Horizons team, and we did not see those types of plumes on Pluto. That's not that big a deal, of course. Maybe the plumes weren't on that day, or wrong time of season, whatever, right? That can be explained. I think more importantly is that there's very limited evidence for analogous fans as well. There are sort of streak features on Pluto, but they're generally much smaller in scale. They're much less numerous. Some of them occur in sort of a nitrogen ice-rich region. Some of them occur outside of it. And some of them are right next to topographic obstacles. And so they're almost certainly, there's very low evidence for these types of features on Pluto. And that's not necessarily saying that the solar-driven model doesn't apply on Triton, but had we found these plumes on Pluto, the relation between them could have been really strong evidence for it. And Mars, Triton, and Pluto are sort of a good group in the sense that those are the only three worlds in our solar system where you have the primary component of the atmosphere is in equilibrium with an icy material on the surface. And so if this was a universal process to this type of atmosphere, you expect it on Pluto. So this is not really an argument against the solar-driven model. It's just more of a discussion point. And so, basically, I think that of all the four sort of main pillars that have been proposed and have been published as sort of the main arguments in favor of the solar-driven model, I don't think any of them are really on solid ground. It's not to say that the solar-driven model isn't viable and isn't a good model. It's just that it's not really any better, in my opinion, than the other models that we have. And so I think that the process responsible for these plumes is yet to be confidently determined, which is great because that motivates a spacecraft mission. And so let's go figure it out, right? All right, so couple things I want to say before I go to the remote sensing tests are that, the cryovolcanic hypothesis, I think, is gaining favor. Some recent arguments in favor of that model are, firstly, that we know cryovolcanism occurs. This isn't a hypothetical process anymore. Enceladus has a cryovolcanic plume. And if you compare the mass flux of the plumes on Triton with those on Mars, so shown here in these two rows, you can see that Triton is orders of magnitude larger than the solar-driven model on Mars, and is actually closer in scale. This comes from work published by Candy Hansen in 2021, is actually much closer in scale to the plume of Enceladus. And, as we understand this new class of worlds, sometimes called ocean worlds, that have these oceans underneath icy material, more and more work going into those types of worlds. As we understand them better, it seems more and more likely that Triton is also an ocean world, and so that maybe a heat source, maybe a source of material, that ocean may be related to cryovolcanism on Triton. So that's, some more recent work on cryovolcanism. Okay, one interesting consequence of the cryovolcanic hypothesis that I just wanted to briefly mention is that if Triton's plumes are cryovolcanic, then either the fans cannot be from the plumes, or the SHG, it really shouldn't be nitrogen rich. It shouldn't be a volatile polar cap. And the argument goes like this, that the plumes are related to the fans, and the fans are related to the SHG, and therefore the plumes are related to the SHG. So A equals B, B equals C, A equals C. If the plumes are cryovolcanic, then the SHG must be related to cryovolcanism in some way. That's a restatement of the above with cryovolcanism. But cryovolcanism itself, it has no sort of preference for nitrogen ice, right? The model doesn't require nitrogen to be there. It's not there, for example, on Enceladus where this is occurring. It's not sort of a key component of the model. And so the fact that the fans are so strongly confined to the SHG, there's clearly, like, that link is clearly established. It implies then that the SHG should not be enriched in nitrogen ice if they're cryovolcanic. The question is, why would they be so confined to the SHG if it's nitrogen ice and it's cryovolcanism? That relation, that strong relation, shouldn't exist according to that model. So that's just kind of an interesting consequence there. Okay, so finished sections 2 and 3 of the outline, and so we're now going to move to the remote sensing tests that we argue could confidently distinguish between these hypotheses. So these tests were developed in the context of the Triton mission concept, which, if you're not familiar with it, it was a flyby mission proposed to NASA. It was not selected, that included imaging, so cameras, and those cameras would also do stereotopography and also a near-infrared spectrometer to measure the composition of the ices. Voyager 2, unlike a lot of spacecraft now, did not have an infrared spectrometer that was capable of measuring composition of Triton's ices, and so that's why we know from the Earth, what ices are there, but we don't have a good sense of where they're located. The concept, of course, had other instruments, but these are the ones that are relevant to these remote sensing tests. And these tests are applicable to other architectures. An orbiter with this type of instruments, of course, could do these tests as well. So what I want to do with the test is not go through them in gory detail, but because we do that in the paper, so it's there, but just kind of give you a flavor for their logic. So one of the tests is related to the composition and the thickness of the southern hemisphere terrains. And basically the argument goes that if the SHT is, clearly a seasonal layer, maybe it's gone completely next time we go there, or maybe it's, decreased dramatically in size, something that's strongly indicating it's a seasonal layer. That's really only consistent with the solar-driven model. It's ruled out the other two, and so it indicates that model. If the SHT is not enriched in volatiles, no nitrogen there, well, the solar-driven model and the volatile ice basal heat model are critically dependent on volatiles. And so a lack of volatiles is good argument for the cryovolcanic model if the SHT is there. If there is enriched in volatiles, well, that's not the cryovolcanic model anymore, like I talked about for the consequence of the cryovolcanic model. So it leaves the solar-driven model or the volatile ice sheet basal heat. And that can be distinguished by the thickness of that ice sheet, because the basal heat model really requires a thick ice sheet in order to cause a lot of insulation. So that would be the solar-driven model. There are outcomes of these tests that are not fully conclusive. Of course, Triton can present scenarios that not every test is fully conclusive, but sometimes they have information like just ruling out one model. And so we include that. These figures are in the paper. So the second test that we proposed is the composition of the fans. So to measure their composition with an infrared spectrometer. If no fans are observed, well, then we can't measure their composition. So that test is neutral. I mean, you could make arguments based on the likelihood of fans being there or not, but they're less definitive than these arguments that we're making. However, if the fans are water ice rich, that is a very strong prediction of the cryovolcanic model, right? It's predicting that these plumes are sourcing material from significantly deeper than just the surface. And so that would be, strong evidence for the cryovolcanic model if the fans were water ice rich. Okay, a third test that we propose takes advantage of the fact that the sun has moved in its subsolar latitude from the time of Voyager 2 to the next mission. So right now, after Voyager 2, the sun, continued moving southward to about 50 degrees latitude, south latitude, and then is now on its way northward. And, for the next century, any mission that goes there will have a very different subsolar latitude than Voyager 2. And so the solar-driven model has this fascinating prediction that the plumes will migrate with the sun. And so if we see evidence, if we see active plumes erupting at a very different latitude near where the sun has moved, that would be very strong evidence for the solar-driven model. Of course, we don't know that plumes are going to be there when we go back. That's fine. The other tests don't depend on active plumes. But if there are plumes that are erupting, then that migration is a great test. In addition to that, if there were plumes at locations without volatile ice, again, the nitrogen ice is sort of critical to two of the models. And so it would rule them out if that nitrogen ice wasn't present, and it would have to be the cryovolcanic model. And then you can apply the same logic to the fans, that, if there's evidence for a significant migration of the fans when, a mission or a telescope could resolve fans on Triton, then it could strongly indicate the solar-driven model if there's, migration with the sun's heating. And then the very last hypothesis test, basically, that we talked about was the fact that the cryovolcanic model could be related to very high surface temperatures, at or near the surface temperature, the melting temperature of water, let's say 270 Kelvin. Of course, there could be antifreezes, and it doesn't have to be a high surface temperature, but it could. The other two models related to nitrogen ice, they're sort of at temperatures at the scale of the melting temperature of nitrogen, or even the boiling temperature, which is way less than the melting temperature of water. So if you have, very significant temperatures like above 200 Kelvin, that would, right at the location of the plumes, that would indicate the cryovolcanic model. And even a near-infrared spectrometer that goes out to sort of the 5 micron range could conceivably detect that type of thermal emission. And that was done with Cassini at Enceladus. So those are the 5 tests. They're independent. Each of them, depends on a different measurement. They're also complementary in the sense that if each of the tests tells you a model and they are agree in that model, that increases, of course, confidence that is really the model that's driving the plumes. They could all rule out all 3 of the models, like each test could rule out one of the different models, and that could tell us that we really, need a new hypothesis. We're not right on the mark with any of those 3. Or even in the unlikely case that Triton actually has 2 different types of plumes, maybe cryovolcanism and the solar-driven plumes do occur on Triton. The tests could indicate that as well, different results from different tests, or even by having different results from different subsets of the fans or plumes. So they're complementary. They're relatively straightforward to implement. A flyby mission with modern day instrumentation could do it. Yeah, that's the test. Thanks, Kim, for the comment. Okay, so before I conclude, there are two more slides that I'd like to discuss. One is that the next few decades, meaning the 2030s and 2040s, are a decently opportune time to be exploring Triton from a seasonal perspective. And there's basically 3 reasons for that. So the first is that the subsolar latitude, which is shown here in blue in time for Triton. So, at 1989, it was 45 south. It has since moved to a little bit south of 50 south. It's actually not that far from 45 south right now, and then is on its way northward for the foreseeable future, for the next century, is eventually going to leave the southern hemisphere terrain within the next few decades. The boundary of the southern hemisphere terrain is a bit fuzzy. I've shown it here with this cyan region because it varies with longitude. It could have changed since Voyager 2. If it's nitrogen ice, and seasonally volatile, that boundary could change. But sometime in this next few decades, the sun will leave that region, and so the heating of that southern hemisphere terrain will be much less. And so, if it is solar-driven plumes, this is really the last opportunity to see those plumes erupting in the southern hemisphere. The existence of an analogous northern hemisphere terrain is unknown. Voyager 2 did not see one, but didn't see the whole northern hemisphere. Certainly, if it's there, it's much smaller than the southern hemisphere terrain, if it's there at all. The 2030s and 2040s are also a good time just for seeing, the whole of Triton, because there's a significant area that goes into polar winter, into this darkness, this, constant darkness in wintertime. It's about 20% of Triton, in the worst case, that it's experiencing constant darkness. For scale, that's, roughly the size of Canada in area. And so that's a big area that would not be observed unless you have instruments that can see in the dark. And so this is just a convenient time from that perspective. It's not necessary because instruments could do it, but it's opportune. And then finally, it's also a time when the lighting of the 2 plume regions, Mahelani and Hilly, is decent. And even if those 2 plumes are not erupting in the next encounter, it's still a very interesting region to see what it looks like. We know we don't have the best imaging of the surface, and getting a sense for that morphology and just getting a sense for the context of that surface could help us to understand the plumes. And the imaging basically is going to get poorer and poorer using solar illumination. If you have a radar or something, then that's different, but using solar illumination is going to get poorer and poorer. And in fact, they will go into constant darkness for decades, eventually, even later on this century. And so it's just kind of a seasonally opportune time. And so we point that out. I view it not as some sort of imperative that we have to go immediately, but as a good motivation. Okay, just wanted to spend a second here advertising another project that I'm on that is not related to Triton's plumes, but is about Triton. I've had fun working on this NASA advanced concept study, looking at if we could land on Triton or Pluto with basically an inflatable envelope to kind of decelerate your lander much faster, use a lot less resources. And if this works, this could be sort of a payload on a much larger orbiter mission, for example, or even its own standalone mission. So just wanted to advertise that. The PI is there if anyone has an interest in that. Okay, so I'll conclude now and just say that there are 3 current eruption hypotheses that we've discussed. In my view, in our view, all 3 of these hypotheses have their pros and their cons. And so the solar-driven model is not necessarily, you know, a clear leader. I think that they're all have good things, and they all have things that, you know, are concerning in terms of making it work on Triton, and there's certainly room for new hypotheses. That's part of the fun. And I view that as a great position to be in, actually, because these hypotheses do make very clear, testable predictions, and so it really motivates another spacecraft mission to go and get that answer. And so I'll stop there, and happy to take any questions. Thanks for your attention.
Yeah, excellent talk, Jason. That was really incredible. Like Kim said in the chat, it was a really great, you know, well-defined and clear set of tests that could definitely form the basis of a mission. So that's really exciting stuff. Folks can go ahead and you know, you can post questions in the chat if you'd like to use the raise hand feature, which I think is maybe under the reactions button on Zoom. You can unmute yourself. And I saw Leslie's comments or question in the chat. I had a similar question too, but yeah, I see that your hand is raised. So go ahead and unmute yourself, Leslie.
Very good talk. Thank you very much, Jason. So are there ground-based observations that you would like to see soon that would either help define a mission's ability to observe plumes, or begin to set a time baseline, for example, or other kinds of observations that would help interpret a mission's observations?
Great question, Leslie. Absolutely. So firstly, I think of the 5 tests that I propose, I think that the first one, the composition and thickness of the SHT, the composition may be measurable by a ground-based observation. You know, it's sort of been hinted at based on looking at the rotation, but a much bigger telescope, and it's not too far in the future, maybe even JWST, could do that measurement because the SHT is so large. And so it could actually, for example, if it says the SHT is there, but not nitrogen, it could actually do that test and maybe even, you know, give us a strong indication there. I think the other 4 tests are much more difficult to implement, and as far as I'm aware, with current telescopes. But there are other things, if I'm allowed to sort of dream, since you asked, you know, for example, a very dense network of occultations, right, could, in theory, pick up a plume on the limb of Triton. And so I would love to see that, since you asked. And then I think, just in addition, the work that's I know to be ongoing, I think you're involved in, but Will Grundy and others as well, you know, keeping track of where the volatiles are moving, what, you know, their presence on the surface and where they're moving, definitely gives us, you know, I don't think that would answer the plume question in that case, but I think it definitely is important information going into any future mission that we do have.
Thank you. There was actually a very dense observation in 2017, and I'll put, dense set of Triton occultations in 2017. I'll put the citation in the chat.
Thank you.
Alrighty, and then we've got another question here in the chat. It says, let's see, have there been any? This is another one of the questions I was going to ask too. So you guys have great questions. Have there been any lab experiments done to test the solid-state greenhouse effect versus cryovolcanism under the conditions expected where the plumes are located for Triton?
Not to my knowledge. Not to my knowledge. It's a great question. I think it's a great idea. I'm not aware of anything that has been done in that regards. You know, aside from, you know, the volatility of nitrogen is known, the transparency of, you know, pure crystal is known, but actually trying to make one of these eruptions, I've never seen anything like that. So that would be awesome, tremendously awesome to see. And it would also really help, you know, the model seems very compelling. And so it would be very fascinating to see if it could produce plumes that can be these monstrous 8 kilometers plumes that we see, or would be smaller features and might tell us that, they're going to be there, but Voyager 2 didn't see them. And there's, different sets of hypotheses. It could really help to just get a sense of the scale, I think, in addition to proving that they actually do occur. Okay, yeah.
Proposal for sure.
Yeah, I don't know. I can't recognize the name from those letters, but I'd love to talk with you. Yeah, my email is just my first and last name at SwRI.org. And or if you put your email in the chat, that'd be great to talk about Mars.
All right, great. Well, we're coming up on the okay, great. We're coming up on the top of the hour here, and so we can kind of wrap things up. Folks have enough time to get to their next meetings. And yeah, like Jason said, you can always email him if you have more questions about things. And we'll try to get the Zoom link working next month. I apologize about that. We'll make sure that it's valid next time. I'm going to triple check ahead of time just to make sure. So thank you everyone for coming. It's great to have you all. And again, thank you so much, Jason, for a really incredible talk.
My pleasure. Thanks, Jody.
Bye, everyone.